Good evening to everyone. Today I am going to present my poster. My poster is the topic is to synthesize different disubstitute dioxidomolybdenum complexes and their transmetallation to form oxidovanadium complexes and their used as biocatalyst. My introduction. In introduction, our focus is to synthesize different managed bases by using ethylene diamine, formaldehyde, and different disubstituted phenol. And these ligands further utilized reaction with molybdenum and vanadium form different disubstituted complexes, and these complexes have been utilized as a catalyst in several reactions like oxidative brunation of phenols, epoxidation of alkenes. Here we have also observed that putting different substituent group at disubstituted phenol may also alter the metal binding in the ligands. And here we have synthesized 12 different complexes. First 4 complexes here we have also saw that complex 1 we have synthesized six different dioxidomolybdenum complex 1 in which complex 6 1, and there further these complexes reacted with vanadium methoxide, and it will give oxidovanadium complexes. And we have also performed reaction of vanadium styrostonate with directly with these ligands, and we have also formed directly these complexes. These complexes utilize as catalysts in several reactions. This is the objective of our work. Here we have saw that this is the ligand, and in ligand, this is the objective of the work. Here we can clearly saw that this is the ligand in which we have first reacted with molybdenum. When R group are tertiary butyl and tertiary butyl methyl, then we obtained dioxidomolybdenum complexes in which metal is bind with one nitrogen, while in case of when R1 and R2 are methyl and chloro, we have obtained dioxidomolybdenum complexes in which metal is bind with two nitrogens. Here we have also saw that when in type 2 complex in which there is steric hindrance in tertiary butyl and tertiary butyl methyl group, there is one pocket remains which we have added one more millimole of one equivalent of molybdenum styrostonate, and we have formed homobinuclear complexes. Later we have also performed the reaction of this mononuclear complexes with vanadium methoxide in ethanol with flux. Our aim is to synthesize heterobinuclear complexes, but when this mononuclear dioxidomolybdenum complexes react with ethoxide, we have observed that there is transmetallation reactions occur with loss of one arm. The possible reason is probable that small size of vanadium and one arm due to loss of one arm, it is more stable, and similarly we have synthesized in transmetallated product vanadium oxidation state is in vanadium is in +5 oxidation state. Similarly we have also synthesized this ligand with vanadium methoxide, and we have synthesized oxovanadium complexes in which vanadium is in +5 oxidation state also. And this is the UV visible spectra of ligand and complexes. In ligand, we have obtained a peak around 2 to 225 nanometer, which is due to pi to pi star transition, and one peak around 280 nanometer, which is due to n to pi star transition. And in complexes, we have saw that along with ligand peak, we have also obtained one additional peak around 350 nanometer, which is due to ligand to metal charge transfer. Due to ligand to metal charge transfer. This is the 1H NMR spectra of synthesized complex 8 oxidovanadium complex. This is the structure of complex. In this NMR, we have obtained 6 aromatic hydrogen in aromatic region, and we have also obtained 6 doublet peaks for this CH2 group. And here we have also saw that we have obtained one peak for NH, which is broad, which confirm that one nitrogen is free, and methyl and tertiary butyl groups are available at their respected deshielded region. This is the NMR of complex mononuclear complex of oxidovanadium, and this is the dioxidomolybdenum complexes. This is the comparative NMR. In the NMR, all the peaks are at respective position, but we have saw that in mononuclear, the peaks due to CH2 group is in the shielded region, but binding to when it binds with another molybdenum, the peaks shifts a little in the deshielded region. Presence of metal is also confirmed with the 15 vanadium NMR. In this spectra, we have saw that there is one peak which confirms that one metal is bound in our cases, while in complex 11 and 12 there is one isomeric mixture is also obtained. Then this is the crystal structure we have obtained in first two structures, shows that metal binds with only one nitrogen. The probable region is due to steric hindrance, while in when R and R dash group are methyl and dichloro, metal is bind with 2 nitrogens. And then we have, this is the crystal structure of oxovanadium complexes, which obtains after transmetallation. And this is the oxovanadium complexes which are obtained after direct reaction of ligand to vanadium. Then these all the synthesized complexes have been utilized for the used as a catalyst in the oxidative bromination of phenols like thiols. In thiols, we have obtained 3 product orthobromo para and orthopara dibromo thiamol using H2O2 KBr and perchloric acid. So firstly, we have our aim to optimize the we have optimized by varying a different amount of KBr, H2O2 and perchloric acid. Our motto is to use minimum amount of these reactant and obtain maximum conversion. So firstly, we are going to take a KBr potassium bromide, H2O2 and perchloric acid, and by using different millimole of catalyst, keeping KBr, H2O2 and perchloric is constant. In 2 hours, we have obtained conversion 42, 48 and 52% by selectivity, and this is the selectivity. And similarly, we have also vary later keeping one constant and varying other, like later we have catalyst we have optimized here entry number 1.38 into 10 to the power minus 3 millimole of catalyst. Later we vary KBr keeping other constant, and later we vary H2O2 and other. Entry number 8 is the best suited result in which 20 millimole of H2O2 KBr and 20 millimole of perchloric acid by using 1.38 into 10 to the power minus 3 millimole catalyst. In 1 hour of reaction time, we have obtained a 90% conversion with the turnover frequency 7,000, around 7,000. With the selectivity, ortho product is 10%, while para is 50%, and disubstituted product is 40%. When we perform this reaction without catalyst, we have saw that in 1 hour we have obtained only 80%, which shows our complexes serve as a good catalyst. Then this is the GCMS of our thymol bromination, in which when we recorded GCMS, we saw that first peak which is due to thymol, and later we obtained peaks due to orthobromo thymol and para, and later we obtained 2 for the dibromo thymol, which we confirmed from the dictionary of GCMS instrument. This is we have also performed that titration in which oxido-peroxido species form, which is formed during the catalytic reactions. Here 2 isobastic peaks are obtained around 331 and 732 nanometer which is the equilibrium point of oxido and oxidoperoxido vanadium or molybdenum complexes. And then summary, we have synthesized here different different tetrabasic hexadentate ligand by varying their substitution at phenolic position. We have obtained different type of complexes which is oscillated and characterized by different techniques, and we have also obtained their crystal structure, and later we have performed their transmetalation and formed their oxidovanadium complexes. All these synthesized complexes have been successfully utilized in the oxidative formation of thymol and different phenol. This work has been published in EGIC, and this is the references. Yeah, thank you. If anyone has any question, please ask me.
Floor is open for the questions. If anyone have the questions.